The signal arrived on a Monday morning in September 2015, and for 0.2 of a second, the geometry of the planet rang like a struck bell. 4 kilometers of laser-mirrored vacuum in Louisiana flexed by less than the width of a proton. 3,000 kilometers away, the same flex repeated in Washington state, 7 milliseconds later. Two black holes, 29 and 36 times the mass of the Sun, had spiraled into each other 1.3 billion light-years from Earth. The chirp was real, and almost nothing about it should have existed. That is the part the headlines softened. You were told this was Einstein vindicated. You were told this was a triumph of human listening. Both true, both incomplete. Because the same signal that confirmed general relativity also confirmed that our model of where black holes come from is broken. The masses were wrong. The frequency was wrong. The implication was wrong. We were not catching up to the universe. We were learning in real time how little of it we had ever been hearing. Wherever you are watching from tonight, whatever hour it is for you, I want you to do something simple for a moment. Tell me in the comments where you are, the city, the country, the time on your clock. Because what I am about to walk you through is a story about distance, and about how the only thing protecting all of us from the loudest events in physical reality is the simple accident of how far away they happen to be. This is the story of the chirp. This is the story of what the chirp was really telling us. When LIGO announced the detection in February of 2016, the framing was almost ceremonial. A century after Einstein predicted gravitational waves on paper, we had finally heard one. The Nobel Prize arrived in 2017. The textbooks updated. The public understood, vaguely, that something important had been confirmed. And for most people, the story ended there. The chirp was a check mark. But under that check mark, the data was already misbehaving. Black holes of 29 and 36 solar masses are not what stellar evolution predicted from the kinds of stars we thought formed them. They were too heavy. They were the wrong shape of merger. They were detectable at a rate that would, within a few years, embarrass every prior estimate. And in 2019, a signal called GW190521 arrived carrying black holes of 66 and 85 solar masses. Squarely inside a region of mass our best theory said should be empty. Not rare, empty. Stars in that range were supposed to obliterate themselves in pair instability supernovae and leave nothing behind at all. The press release version of this story is that we confirmed Einstein. The slower reading is that we discovered we do not understand the population of objects we just learned to hear. And the signal we caught was not the loudest one out there. It was just the first one we were listening for. The question is what we missed and what is still coming. The official version of the story was elegant. It had to be. When you announce a discovery a century in the making, you do not lead with the part where the data breaks your model. You lead with the part where the math holds. And in February 2016, the math held beautifully. Einstein's general relativity had predicted that accelerating massive objects should radiate ripples in spacetime itself. 100 years later, LIGO had caught one. The Nobel Prize followed. The story became, in the public imagination, a clean confirmation of a clean theory. Read the actual papers and the tone shifts. The collaboration's own peer-reviewed work used careful, conditional language about the masses involved. The press releases used celebratory language about the detection. Those are two different documents doing two different jobs. One is reporting what the instruments measured. The other is protecting public trust in a field that was about to ask the public to fund decades more of expensive listening. Here is what the careful language was holding back. Stellar evolution, the theory that describes how stars live and die, predicts a fairly narrow range of black hole masses from collapsing stars. Most should fall under about 20 solar masses. Above that, the physics gets strange. And in a band roughly between 65 and 130 solar masses, the theory says black holes should not form at all, because stars that large destroy themselves in a runaway thermonuclear process called pair instability collapse. No remnant, no black hole, just a brilliant total disassembly. GW150914 sat at the edge of what the theory could tolerate. GW190521 sat squarely inside the forbidden zone. And the detection rate that followed those two events made clear they were not anomalies. They were the population.
This is the part that should bother you. Not that the science was wrong. Science being wrong is how science works.
The problem is the gap between what physicists were quietly saying in their papers and what the public was being told to celebrate. The same arc has happened before. Dark matter was, for decades, a small correction to galactic rotation curves. Then it became 85% of the matter in the universe and a complete mystery. Confirmations in physics have a habit of opening doors the headline never mentions. You were told Einstein was right. He was. You were not told that being right about the ripples did nothing to tell us what was making them. That question is still open, and every new detection makes it harder to close. To understand why this detection should disturb you more than it impressed you, we have to understand what a black hole actually is. Not the cartoon, not the funnel, not the swirling drain in space. The real thing. Because almost everything you think you know about that is wrong. A black hole is not an object. That is the first thing to unlearn. There is no surface to land on, no shell to break through, no dark sphere hanging in space waiting to be approached. A black hole is a region of spacetime so steeply curved by concentrated mass that no path through it leads back out. The boundary we call the event horizon is not a wall. It is the last surface where the geometry of reality still permits return. Cross it, and every future direction you could possibly travel points further in. When two of these regions spiral into one another, they do not collide the way two stones would. They distort each other. They drag space-time around themselves like fabric caught in a current. And in the final fractions of a second before they merge, they orbit at a measurable fraction of the speed of light, radiating the energy of their motion as gravitational waves. Actual deformations of the geometry around them, traveling outward at light speed in every direction. In GW150914, that radiation amounted to roughly 3 solar masses of energy released in less than a second. 3 suns converted directly into gravitational waves. The instantaneous power output exceeded the combined luminous output of every star in the observable universe, briefly. And then it was over, and the wave kept traveling. For 1.3 billion years it traveled. It crossed galaxies. It passed through stars. It passed through Earth in 2015 and stretched the planet by an amount smaller than a proton. And the only thing on the surface capable of noticing was a pair of instruments tuned specifically to that exact range of stretch. Think about that for a moment. Space-time is not a metaphor. It is the floor you are standing on. It is the distance between your eyes and this screen. A gravitational wave is that floor briefly becoming liquid. You were inside the wave, So was every person reading this. So was every atom of your body. You were deformed, and you were unmade, and you were put back, and you never felt a thing. Because the wave had been traveling so long that what reached us was the faintest echo of an event that, closer in, would have been catastrophic. Einstein himself was unsure whether these waves could ever be detected. Some of his letters suggest he hoped they could not. He understood, perhaps better than anyone, that the universe being able to ring like this meant the universe could be rearranged by it. We built an instrument that could finally hear the universe, and the very first thing it told us was that we had been deaf for the entire history of our species. The question is, deaf to what? Here is where the science gets honest about what it does not understand. The mass gap is not a small theoretical inconvenience. It is one of the most carefully predicted features of stellar evolution. Above roughly 65 solar masses, the cores of dying stars reach temperatures where photon energies become high enough to spontaneously create electron-positron pairs. That conversion robs the core of the radiation pressure holding it up. The star collapses, ignites uncontrollably, and tears itself apart in a pair instability supernova that leaves no remnant. No black hole, nothing. Above roughly 130 solar masses, the collapse becomes total and a direct black hole is possible again. Between those two values, the theory says nothing should exist. GW 190521 ignored the theory. The two black holes that merged in that signal weighed in at 66 and 85 solar masses, both inside the forbidden band. And follow-up detections have continued to find objects sitting where the model says they cannot form. This is not a measurement error. The masses are reconstructed from the waveform itself, and the waveform is a direct consequence of general relativity. The objects exist. The theory is the part that has to bend. So physicists have started bending it, carefully, in several directions at once. One possibility is hierarchical merger. Smaller black holes, formed within the allowed range, collide and produce a heavier black hole. That heavier black hole later finds another partner and collides again. The result is a population of objects whose masses do not reflect the stars that originally collapsed, but the cumulative history of previous mergers. In dense stellar environments, globular clusters, the cores of galaxies, the gas-rich disks around supermassive black holes, this kind of recursive accumulation may be common. Another possibility is older. Primordial black holes, formed not from stars at all, but from density fluctuations in the first second after the Big Bang, before any star had ever existed. Their masses would not be bound by stellar physics, because no star was ever involved. If a small fraction of dark matter is made of these objects, the detection rate begins to make sense. A third possibility is environmental. Accretion disks around supermassive black holes are thick, turbulent, and crowded. They may act as factories, concentrating smaller black holes, feeding them gas, and driving them into mergers that would never happen in open space. Each explanation rewrites a different part of the textbook. Each one means the universe contains a population of objects whose origins either predate or violate the rules that built every star, every planet, and every chemical element you have ever touched. If these black holes formed by eating others, then we are looking at predators in the dark. And predators imply a hunting ground we have not yet mapped. Before LIGO turned on, the prediction for detectable mergers ranged from roughly 0.4 to 400 per year, depending on which formation model you trusted. That spread alone tells you how little anyone really knew. The lower estimates assumed a quiet universe. The upper ones assumed a busy one. Almost no one expected what actually happened. By the end of the third observing run, LIGO and Virgo had catalogued nearly 90 confirmed mergers. By the fourth run, currently underway, the rate has climbed to roughly one detection every 2 to 3 days. The cumulative catalogue has now crossed 200 events and is still growing. And these are only the mergers we can hear with current sensitivity, in the frequency band these particular instruments are tuned to. Scale that forward. If the detectors we have can hear a merger every few days, out to a fraction of the observable universe, the implied rate across the full observable volume is closer to one merger every few minutes. Not per year, per minute. Somewhere, right now, while you are reading this sentence, two black holes are spiraling into each other and releasing the energy of several suns in less than a second. By the time you finish this paragraph, several more have happened. By the time this video ends, hundreds. This is not a richer cosmos. This is a cosmos whose dark population vastly exceeds its luminous one. The stars we see, the constellations, the Milky Way, every visible point of light in the sky, are a thin foam on top of a black ocean. The ocean has been there the whole time. We just learned to dip a single instrument into it. And here is the part that should bother you. The mergers we hear are the loudest ones. In the narrowest band our detectors are tuned to. Anything quieter, slower, or stranger passes through us undetected. Supermassive black hole mergers, the ones involving objects millions of times the mass of the Sun, radiate at frequencies LIGO cannot reach. Pulsar timing arrays have only recently started catching the background hum of those events. The full spectrum of gravitational waves spans frequencies we cannot yet measure with any single instrument. The waves are passing through you now. They have been passing through your ancestors, through every generation of life on this planet, for as long as Earth has existed. They will keep passing through your descendants forever. The universe has been doing this in silence for 13.8 billion years. We had no idea. If this is the rate of mergers we can hear, what is the rate we can't? And what does it mean that the silence we grew up inside was never silence at all, only deafness? Distance is doing all the protective work. When GW 150914 stretched LIGO's 4-kilometer arms, the displacement was on the order of 10 to the negative 18 meters, 1,000th the diameter of a proton. That is the strain after the wave traveled 1.3 billion light-years. The energy density of the wave falls off with distance, but the strain itself falls off more slowly, and at close range, the same physics that registered as a faint chirp on Earth would do something very different to anything in its path. Move the same merger closer.
At a distance of a few thousand light-years, still inside our galaxy, the strain on the human body would become physically measurable. Your bones would resonate at audible frequencies during the passage of the wave. Buildings would creak. Sensitive instruments would saturate. The merger itself, billions of years old at that point in the cosmic timeline, would announce itself through the structural integrity of everyday objects. Move it to a light year away, and the geometry of your body becomes the problem. A close gravitational wave does not kill with radiation. It kills by briefly making you the wrong shape. The forces that hold your atoms together, electromagnetic forces mostly, are extraordinarily strong, but they assume a stable background geometry. When the geometry itself oscillates fast enough and hard enough, that assumption breaks. Tissue does not tear from heat. It tears from being asked to occupy two slightly different lengths at the same time. Move it closer still, into the orbital neighborhood of a planet, and the planet itself becomes the wrong shape. Tidal forces that we normally associate with the immediate vicinity of an event horizon, the spaghettification you have heard about, extend outward in a softer form during a merger. Crusts crack, atmospheres slosh, magnetic fields warp. We have no record of a merger happening this close to Earth. The probability over any human timescale is vanishingly small. That is the comfort. That is also the only comfort. Compare this to other cosmic threats we already take seriously. A nearby gamma-ray burst, within a few thousand light-years, could strip the ozone layer and trigger a mass extinction. A supernova at similar range could do the same. We map those candidates carefully. We track them. We have no equivalent map for nearby black hole pairs that might one day merge, because we have not yet developed the instruments to find them in the in-spiral phase. We have catalogued the mergers we can hear from billions of light-years away. We have not seriously catalogued what is forming in our own galactic backyard. That gap is not science failing, it is science being early. But early is not the same as safe. Our entire ability to hear the universe ringing depends on a handful of extremely fragile machines on a single planet. LIGO Hanford and LIGO Livingston are the two American detectors. Each one is an L-shaped vacuum tunnel 4 kilometers long per arm. The mirrors at the ends of those arms are suspended in multi-stage pendulums to isolate them from ground vibration. The vacuum inside is one of the emptiest volumes on Earth, lower pressure than the surface of the Moon. The laser beams that bounce between the mirrors are stabilized to a precision that allows the detection of length changes smaller than a proton. Add Virgo in Italy and Kagra in Japan, and the entire global network of operational gravitational wave observatories fits in a short list. That is the listening infrastructure for the universe. A truck driving past Livingston has, on more than one occasion, temporarily blinded the detector. A magnitude 4 earthquake on the other side of the planet introduces noise that takes hours to filter out. Construction in the wrong county has corrupted observing runs. The instruments are calibrated to such precision that the ordinary motion of the planet, tides, wind, the seasonal flexing of the ground, has to be modeled and subtracted from the data continuously. And these instruments only cover a narrow frequency band. LIGO is most sensitive between roughly 10 and a few thousand hertz, which is where stellar mass black hole mergers happen to live. Mergers of supermassive black holes, the ones at the centers of galaxies, millions of times heavier, radiate at frequencies far below that and require entirely different instruments to detect. LISA, the space-based observatory planned for the mid-2030s, will cover part of that low-frequency band. Pulsar timing arrays like nanograv cover an even lower band, using the regular pulses of distant neutron stars as a galactic scale ruler. Each instrument hears a different octave of the same cosmic instrument. No single one hears the whole thing. Imagine being the only species in known history to develop hearing, and using it once a week, in one ear, in one room, while standing next to a busy highway. That is roughly the situation. We are not watching the universe. We are pressing a single ear against a closed door and trying to interpret the muffled rhythm on the other side. Funding gaps, political shifts, and natural disasters all threaten this thin layer of capability. A single fire, a single budget cut, a single broken mirror could take a detector offline for years. The instruments are extraordinary. They are also exposed. If we are this limited and the universe is this loud, then someone has to ask the obvious question. Why has the official framing of all this remained so calm?
Read the LIGO collaboration papers, and you will find some of the most carefully chosen sentences in modern physics. Read the press releases that accompany those same papers, and you will find a different voice entirely. The papers say things like, the formation channel for these objects remains uncertain. The press releases say the universe is rich and varied and full of wonders. Both statements are true. They are also doing very different work. The first is admitting that we do not know what produced the objects we just detected. The second is protecting public trust and the funding pipeline that keeps the detectors running. This is not a conspiracy. It is important to say that clearly. The physicists working on these instruments are not lying. They are doing what good science demands. refusing to overstate what the data shows, refusing to alarm the public over models still being argued in conference rooms, and refusing to let speculation outrun evidence. That restraint is one of the reasons modern physics is trustworthy at all. But there is a cost to that restraint. When a paper says the formation channel remains unclear, it means, in plainer language, that we do not know what is making these objects. We have several candidate explanations. None of them have been confirmed. Some of them, if confirmed, would rewrite parts of cosmology. That is a sentence the public should sit with longer than it has been allowed to. The same softening happens around the mass gap. The same softening happens around the detection rate. The same softening happens around what fraction of dark matter might be made of primordial black holes. Each time, the careful institutional voice translates a genuinely destabilizing finding into language that sounds like progress. Most people have never been told that the universe contains things our best theories cannot account for. Most never will be, because the framing stays optimistic by default, and because there is no incentive structure inside science communication for sitting with uncertainty in public. The papers do it. The conferences do it. The textbooks eventually do it. The public-facing story almost never does. This is the gap, not between truth and lie, between what is known to be uncertain and what is communicated as resolved. The chirp arrived in 2015. The mass gap problem became undeniable in 2019. We are now in 2026, and the public conversation about gravitational waves still mostly stops at Einstein was right. So if the science is uncertain and the messaging is careful, what is the bigger picture they are circling but not naming? That is the question the next chapter has to answer, because the answer changes everything you thought you knew about where you live. Black hole mergers are not the story. They are the receipts. The story is much larger and much older and considerably more uncomfortable. The visible universe, the stars, the galaxies, the gas, the dust, every photon ever emitted and every chemical element ever forged, accounts for roughly 15% of the matter we can measure gravitationally. The other 85% is dark matter, a substance that interacts gravitationally but emits no light, absorbs no light, and has so far resisted every attempt at direct detection. We know it is there because galaxies rotate faster than their visible mass should allow. We know it is there because the cosmic microwave background carries its imprint. We know it is there because the universe's large-scale structure cannot be explained without it. We do not know what it is. Layered on top of this is the population of black holes, stellar mass ones, intermediate mass ones, and the supermassive ones that anchor the centers of nearly every large galaxy, including ours. Sagittarius A star, the 4 million solar mass object at the center of the Milky Way, has been imaged. M87 star, the 6 billion solar mass object at the center of a galaxy 53 million light-years away, has been imaged. Both confirmed what the math had predicted. Both raised harder questions about how objects that large grew in the time available. The James Webb Space Telescope has only deepened the puzzle. It has found supermassive black holes already in place when the universe was less than 1 billion years old. Too large, too early for the standard slow growth picture to explain. Something accelerated their formation. We do not yet know what. Add to this the possibility that some fraction of dark matter is itself made of primordial black holes, and the picture sharpens into a single, uncomfortable shape. The cosmos described in textbooks, luminous, mappable, ordered, is a minority report. Most of what exists in this universe, most of what gravitates, most of what shapes the motion of every star and every galaxy is dark, silent, and not yet understood. Black hole mergers are simply the rare moments when this hidden majority becomes briefly audible. Every star chart, every constellation, every navigational system, every cosmological story we have ever told as a species was built on the visible 15%. The other 85% has been pulling on us the entire time. You live inside a structure whose load-bearing walls you have never seen and cannot prove the shape of. Now imagine learning that those walls are made of things that occasionally collide. And this is where the comfortable framing finally collapses. Because if the dark inventory is this large and this active, then one final question becomes unavoidable. The first detection of merging black holes was not a triumph of human ingenuity. It was the moment the universe finally got loud enough that we could no longer pretend we were alone in a quiet cosmos. Look at the case the way it has assembled itself across these chapters. The chirp arrived in 2015, and the masses were already wrong. The mass gap problem deepened in 2019, and the objects kept arriving from a region of mass our theory said should be empty. The detection rate accelerated past every prior prediction, implying a cosmic merger every few minutes across the observable universe. The bodies we ourselves are made of would not survive a close approach by the same physics we have learned to hear from billions of light years away. The instruments doing the hearing are fragile, narrowband, and concentrated on a single planet. The institutional voice describing all of this has stayed careful and optimistic, in part because the public has never been prepared to hear what the data is starting to suggest. And underneath all of it sits the larger fact that the visible cosmos is the minority, and the dark inventory we are only beginning to map is the majority of everything that physically exists. Now go back to the chirp, 0.2 of a second, a signal so faint it stretched the planet by less than a proton. A pair of black holes that should not have existed, merging into a single black hole that radiated 3 suns worth of energy in less time than it takes a human heart to complete one beat. That was not a discovery, that was a message. The first sentence in a language we have only just learned to recognize. We have heard hundreds since. We will hear millions. And every one of them rewrites a piece of the story we told ourselves about where we live. The black holes are not out there. They are part of the same physical universe as your kitchen, your bones, your children. The waves they make pass through all of it equally. The protection you live inside is distance, nothing more. This is not a call to fear. It is not a claim that science has failed. It is not an argument against exploration. The same instruments that revealed the danger are the ones that may, eventually, let us understand it. We are not powerless. We are simply earlier in the story than we thought. We thought we were listening for confirmation. We were listening for the warning, and it has only just begun.